So for homework number 2, we chose to do problem number 2 as described here. And starting off with our work, what we basically realized is that this is going to be a square waveform, and in order to represent that, it's going to pretty much be a piecewise defined function as described here, for the first interval being from 0 to half a millisecond and from half a millisecond to 1 millisecond. Now, to do the integration of this, we used the integrated formula, which is V output of t is equal to -1 over RC times the integral of the input waveform with respect to time. So, doing that for the first interval, over here, what we have is we have V output of t is equal to this, and after doing some simplification, we eventually end out with V output of t is equal to -1000 t, which is in seconds. So, inputting our first value of 0 seconds, we obviously get 0 volts.
This point.
And then for our second in value, which is the half a millisecond, which is represented here, we get -0.5 volts.
-0.5, this point.
So, we do the same exact thing, but for the second part of the piecewise defined function, which has a magnitude of -1 volts. So, after doing it represented here and then simplifying it, we end up with an equation of V output of t is equal to 1000 t minus 1. So, inputting our first interval value, which is the half millisecond,
This is where we left off.
we get the -0.5 volts. And for our n value of 1 millisecond, we get 0 volts,
There.
which ends up looking exactly like a triangular waveform. Then, for the second part of the problem, it asks us to do the exact same thing. It's just that now, this time, the input waveform has a peak value of 2 volts and a negative peak value of -2 volts. So, doing the exact same procedure, we set up the piecewise defined function with the same intervals from 0 to half a millisecond and from half a millisecond to 1 millisecond, and then setting up the first interval here and then simplifying, we get that our equation is V output of t is equal to -2000 t. So, inputting our first interval value in, we have V output of 0 equals 0 volts, which is right here, and then we have our second interval value of half a millisecond, which turns out to be 1 volt, represented here. Then we do the same exact thing for our second part of the piecewise defined function, just like before, and we get our V output of t is equal to 2000 t minus 2. So, putting our first interval value in of half a millisecond, we get -1 volts, which is the exact same value as our n value of the previous interval, and then we get that our final n value of 1 millisecond is equal to 0 volts, represented here, which it looks exactly like the same triangular waveform as the first part. It's just that now that the negative peak value was -1 volts as opposed to half a volt.
The scale
Or
on the
negative
left
half.
has changed.
So,
And now for the third part, what we're doing is we take the same square wave, and only this time we assume that as amplitude of plus 2 volts and period of 2 milliseconds, so the period has doubled. And what we do, of course, is we break this into a piecewise function again for periods, this time from 0 to 1 millisecond and from 1 to 2 milliseconds. So, V0 is 0, that's what we're given. So we want to find V out at 1 millisecond. We take this integral function. I've done the liberty of plugging in all the values already. We take this integral and we end up with -1 volt, which would be this point. And then we can't directly take the integral to find the second point, so we take the difference between V out at 2 milliseconds and V out at 1 millisecond, and that equals this integral with all the values plugged in. After we do the math, we end up with +1 volt, and then since it's +1 volt from this point, it is -1 volt plus 1 volt equals to 0 volts at 2 seconds, and that would be this point here. So once again, it is a triangular waveform that looks very much like what we had before, only this time the period is 2 milliseconds. Of course, the amplitude is still 1 volt.